Our Sun began as a vast cloud of gas and dust, a nebula collapsing under its own gravity. This contraction increased density and temperature, setting the stage for nuclear fusion. As the core reached 15 million degrees Celsius, hydrogen atoms began fusing into helium, releasing tremendous energy. This marked the birth of our Sun as a main sequence star. The core is where fusion happens. It's immensely hot and dense, generating almost all of the Sun's energy. Photons take hundreds of thousands of years to escape from here. Energy from the core slowly radiates outwards. Through the radiative zone, photons are constantly absorbed and re-emitted, making the journey slow and chaotic. In the convective zone, energy is transported by the bulk movement of hot plasma. Hotter plasma rises, cools, and then sinks back down, creating convection cells. The photosphere is the Sun's visible surface. Granules, the tops of convection cells, give it a mottled appearance. It's cooler than the core, around 5,500 degrees Celsius. Sunspots are cooler, darker areas on the photosphere caused by intense magnetic activity, inhibiting convection. They appear in cycles linked to the Sun's magnetic field. The chromosphere is a thin reddish layer above the photosphere, visible during solar eclipses. It's hotter than the photosphere, exhibiting spicules, jets of plasma. The corona is the Sun's outermost layer, a tenuous, extremely hot atmosphere extending millions of kilometers into space. Its temperature can reach millions of degrees Celsius. Solar flares are sudden, violent releases of energy from the Sun's surface, often associated with sunspots. They emit radiation across the electromagnetic spectrum. GEs are huge expulsions of plasma and magnetic field from the Sun's corona. They can travel outwards at millions of kilometers per hour, impacting planets. The solar wind is a continuous stream of charged particles flowing outwards from the Sun's corona. It affects planetary atmospheres and magnetospheres. Earth's magnetosphere, generated by our planet's internal dynamo, deflects much of the solar wind, protecting us from harmful radiation. When charged particles from the solar wind interact with Earth's atmosphere near the poles, they create the beautiful auroras, also known as the northern and southern lights. The Sun's magnetic field is complex and dynamic, generated by the movement of charged plasma within the Sun. It drives many solar phenomena. The Sun's magnetic activity follows an approximately 11-year cycle, with periods of high sunspot activity, solar maximum, and low activity, solar minimum. Helioseismology studies the Sun's internal structure by analyzing the vibrations on its surface, similar to how seismology studies Earth's interior. Neutrinos, nearly massless particles, are produced in nuclear reactions in the Sun's core. They provide direct information about these reactions. The Sun radiates an enormous amount of energy into space every second. This energy is essential for life on Earth, driving our climate and ecosystems. Variations in solar radiation can influence Earth's climate, though the magnitude of this influence, compared to other factors like greenhouse gases, is a topic of ongoing research. Our Sun is classified as a G-type main sequence star, a yellow dwarf. This classification is based on its temperature, luminosity, and spectral characteristics. The Sun resides in the Orion arm of the Milky Way galaxy, orbiting the galactic center at a speed of approximately 220 kilometers per second. In billions of years, the Sun will run out of hydrogen fuel in its core, causing it to expand into a red giant. This expansion will engulf Mercury and Venus. After the red giant phase, the Sun will shed its outer layers, forming a beautiful planetary nebula. This ejected material will enrich the interstellar medium. The Sun's core will eventually collapse into a white dwarf, a small, dense, and extremely hot remnant that will slowly cool over trillions of years. The Sun is essential for life on Earth, providing the energy for photosynthesis and regulating our planet's temperature. Its stability is crucial for our survival. Solar flares and CNEs can disrupt radio communications, damage satellites, and even cause power grid failures on Earth, highlighting the importance of space weather forecasting. Scientists use a variety of telescopes and space missions to study the Sun, including SOHO, SDO, and Parker Solar Probe, revealing new insights into its workings. The Sun's radiation and solar wind affect all planets in our solar system, shaping their atmospheres, magnetic fields, and even their surfaces over vast timescales. The Sun is more than just a distant star. It's our life source, a dynamic and complex object that continues to fascinate and challenge scientists. Its understanding is paramount to our future.